Distributed consensus is a fundamental concept in blockchain technology. It ensures everyone agrees on the order of transactions. This agreement is crucial for maintaining a single, trustworthy history of the blockchain. Without it, the system would be vulnerable to manipulation. In decentralized networks, there's no central authority. Distributed consensus mechanisms solve this problem. They provide a way for all participants to agree on a single version of the truth. This process is essential for the integrity and security of blockchain systems. It ensures that all participants rely on the same data. Nakamoto consensus is the groundbreaking mechanism behind Bitcoin. It is the foundation that allows Bitcoin to function as a decentralized digital currency without the need for a central authority. It combines proof of work with a specific set of rules to achieve consensus. This ensures that all participants in the network agree on the state of the blockchain, maintaining its integrity and security. Proof of work, or PoW, requires participants, called miners, to solve complex mathematical problems. These problems are cryptographic puzzles that require significant computational power to solve. These problems are difficult to solve but easy to verify. Once a miner finds a solution, it can be quickly checked by other nodes in the network, ensuring that the solution is valid. The first miner to solve the problem gets to add a new block of transactions to the blockchain. This process is known as mining, and it is essential for the creation of new bitcoins and the validation of transactions. This process is computationally intensive, requiring significant energy. Mining farms, which are large data centers filled with high-powered computers, are often used to increase the chances of solving these puzzles. However, it provides robust security. The computational effort required to solve these puzzles makes it extremely difficult for any single entity to alter the blockchain, ensuring its immutability. Miners receive rewards for their work in the form of newly minted bitcoins and transaction fees. This reward system incentivizes miners to continue participating in the network and securing the blockchain. This incentivizes participation and network security. As more miners join the network, the overall security of the blockchain increases, making it more resilient to attacks. The difficulty of the puzzles adjusts over time. This adjustment mechanism ensures that blocks are added to the blockchain at a consistent rate, regardless of the total computational power of the network. This ensures consistent block generation times regardless of network hash rate. By maintaining a steady rate of block creation, the network remains stable and predictable, which is crucial for its long-term viability and trustworthiness. Proof of stake, or PoS, offers an alternative to proof of work. Instead of computational power, PoS relies on economic stake. In a PoS system, validators propose and validate blocks based on the number of coins they stake or lock up as collateral. The more coins staked, the higher the chance of being selected to validate a block. This mechanism consumes significantly less energy than PoW. It also aligns incentives by making attacks economically irrational. If a validator acts maliciously, they risk losing their staked coins. This economic disincentive strengthens the network security. Proof of burn, or PoB, presents a unique approach to consensus. In PoB, participants burn coins by sending them to an unspendable address. This act demonstrates commitment to the network. The more coins a participant burns, the higher their chances of gaining validation rights. PoB, like PoS, is more energy efficient than PoW. However, it introduces the concept of virtual mining rigs based on burned coins. This mechanism can be seen as a bridge between PoW and PoS. The act of burning coins represents a long-term investment in the network security. Section 5. The role of difficulty levels. Difficulty levels play a crucial role in blockchains like Bitcoin. They ensure consistent block generation times despite varying computational power. As more miners join the network, the hash rate increases, potentially leading to faster block generation. Difficulty adjustments counter this by making the cryptographic puzzles harder to solve. This dynamic adjustment maintains a predictable block interval. This predictability is essential for network stability and security. Difficulty levels are a fundamental aspect of blockchain's self-regulating mechanism. Section 6. Combating Sybil attacks. In this section, we will delve into the intricacies of Sybil attacks and explore the various strategies employed to mitigate their impact on decentralized networks. Sybil attacks pose a significant threat to decentralized networks. These attacks involve malicious actors creating numerous fake identities or nodes to gain disproportionate influence over the network. Attackers create multiple fake identities to gain control of the network. By doing so, they can manipulate the consensus process, disrupt network operations, and potentially double spend or censor transactions. Consensus mechanisms like proof of work and proof of stake provide effective defenses against Sybil attacks. These mechanisms are designed to make it economically and computationally challenging for attackers to create and maintain a large number of fake identities. In proof of work, the high cost of computational power makes creating a large number of identities economically infeasible. Miners must solve complex mathematical puzzles which require significant computational resources and energy consumption. In proof of stake, the requirement to stake a significant number of coins acts as a deterrent. Validators must lock up a substantial amount of cryptocurrency as collateral, which they risk losing if they act maliciously. Attackers would need to control a large portion of the staked coins to influence the network. This makes it prohibitively expensive for any single entity to gain control, as acquiring such a large amount of cryptocurrency would be financially unviable. These mechanisms ensure that a single entity cannot easily dominate the network. By distributing control and requiring significant investment, they create a robust defense against Sybil attacks. They contribute to the resilience and security of blockchain systems. By maintaining a decentralized and secure network, these consensus mechanisms uphold the integrity and trustworthiness of blockchain technology, ensuring its continued growth and adoption in various industries. Section 7. Energy utilization and efficiency. In this section, we delve into the critical issue of how energy is utilized within blockchain technologies and the efficiency of these processes. Energy consumption is a significant concern, particularly for proof-of-work blockchains. These systems require vast amounts of computational power to solve complex mathematical problems, which in turn consumes a substantial amount of energy. The computational power required for mining consumes a substantial amount of energy. This energy is often sourced from non-renewable resources, leading to a considerable carbon footprint. The cooling systems needed to maintain optimal operating temperatures for these processors further add to the energy burden. Proof of stake and proof of burn offer more energy-efficient alternatives. These consensus mechanisms do not rely on energy-intensive mining processes. Instead, they use different methods to validate transactions and secure the network. By relying on staked coins or burned coins, they eliminate the need for energy-intensive mining. In proof of stake, validators are chosen based on the number of coins they hold and are willing to stake as collateral. In proof of burn, participants burn or destroy coins to gain the right to mine or validate transactions. This difference in energy consumption has sparked debate within the blockchain community. Proponents of proof of work argue that its high energy consumption is justified by the robust security it provides. Critics, however, point to the environmental impact and advocate for more sustainable alternatives. While proof of work provides robust security, its environmental impact is a growing concern. The high energy consumption contributes to greenhouse gas emissions and environmental degradation. This has led to protests and calls for the industry to adopt greener practices. The search for more sustainable consensus mechanisms is an ongoing area of research and development. Researchers are exploring various approaches to reduce the energy footprint of blockchain technologies. This includes the use of renewable energy sources, more efficient algorithms, and entirely new consensus mechanisms that prioritize sustainability without compromising security. Section 8. Beyond the basics, smart contract innovations. Blockchain technology extends beyond simple cryptocurrencies. Smart contracts, self-executing contracts on the blockchain, have opened up a world of possibilities. Layer 2 solutions built on top of existing blockchains offer improved scalability and efficiency. They handle transactions off-chain, reducing congestion on the main blockchain. Sharding is another innovation that enhances scalability. It divides the blockchain into smaller, more manageable partitions, allowing for parallel processing of transactions. These advancements are pushing the boundaries of what's possible with blockchain technology. They are paving the way for more complex and sophisticated applications. Section 9. Conclusion: the future of consensus. Distributed consensus mechanisms are the backbone of blockchain technology. They ensure the integrity, security, and reliability of decentralized networks. From the groundbreaking Nakamoto consensus to the innovative proof of stake and proof of burn, these mechanisms continue to evolve. Each approach comes with its strengths and weaknesses. As blockchain technology matures, we can expect further advancements in consensus mechanisms. These advancements will drive greater adoption, scalability, and innovation across industries. The future of blockchain is intertwined with the development of more efficient, secure, and sustainable consensus mechanisms.